Okay, so this is the second lecture of week 1. We're going to do it online exceptionally today. And I apologize for the late notice, but hopefully the video will be up soon and we will get up to speed in this lecture. Okay, so let's just recap. Let's just recap what we were talking about. We were talking about sets, and again, set is a collection of actually an unordered collection of objects, and the objects can be the same, the objects can be different. You can have only numbers and symbols, whatever kinds of objects you want. If you kind of group them in an unordered way, you have a set. We also saw some mathematical statements regarding sets. The first statement we saw was this one. So this statement means the element x, right, or the little x is an element of the set A. Okay, remember that we assign capital letters to sets. Okay, or when x is not in A, we say we write like this. Okay, so this is one mathematical statement. Actually, two of them. The other kind of statement that we came across is between sets. It's a question or a comparison between sets. Imagine that you have a set A and a set B, and when you say this, it means that A is totally contained in B, or A is a subset of B. So is that B embraces, B kinds of encompasses A. And if it's not totally contained, we just cross the symbol that way. Okay. What else did we see? Well, we started seeing operations. Okay. We started seeing operations. In this case, it's not arithmetic operations, but set operations. And the first operation that we studied was the union operation. Okay, and we saw that A union B means take all elements of set A and all elements of set B, just put them all in the same bucket and just hard copy everything that is in A and in B. So just take it all. So this is what it means. So the union is just take it all. Okay. Again, so that we just kind of recap, this is an operation in between two sets, right? So this set is in the left-hand side. This A is a set. In the right-hand side, this B is a set, and the operation will give you a new set. You can call it C, S, P, whatever you want, but this overload notation here, it's overloaded, so you have like 3 letters, but this is actually a new set. Okay. All right. So we stopped like here, where we kind of defined the union operation. We said that there's like a natural language or a colloquial word for union. We usually say or. So so every element of the union is either in A or B. So when I say A or B, if you hear this in English language, you should automatically translate this to the math language as A union B. Okay, and just to recap, we saw, like, this is an example that we've done, where we have a set A and a set B, and the union is just taking it all, hard copying A, hard copying B, and again, because sets are an ordered collection of objects, I don't need to repeat the object, right? So for example, when I'm hard copying B, I don't need to copy 5 because 5 was already copied from A. Okay, so, and it doesn't matter the order. If you kind of did this way, as long as the elements are the same, your union is correct. Okay. All right. So in terms of the Venn diagram, it's if you think about it, we're generating a new set. If I were to kind of highlight the set would be this orange part here. It's the whole thing. It's just embracing A, B, and like whatever is in A will be copied, whatever is in B will be copied. Okay? All right, so now what I want to do is I want to talk about some properties of the of this operation. Okay, so just as it happens in arithmetic, let me move this up just a bit. Just let me move this here just a little bit. Okay, so just as it happens in arithmetic, where operations have property, right? So for example, let's say that the addition operator. So the addition operator is operating in two numbers and it's resulting in a different number, okay? And this addition, this operation, so 1 plus 2 is an operation on this both these two numbers, and it's resulting in 3. It has a special property that you can kind of change the order, right? So it doesn't matter if you take 1 plus 2 or 2 plus 1, both of them will equal 3. So this property, and now I'm just going to put it this way, so 1 plus 2 is equal to 2 plus 1, both of them result 3. This characteristic, this property of the addition operation is called the commutative operation property. So if you think about this, the set operation of union, it's exactly the same thing. It doesn't matter if you're if you write like first uniting A and if you write that you're uniting A union B, it's the same thing as uniting B union A, right? So let's give you an example. So let's make this let's do the hard copy operation in sequence. So this is the set A, it's 1, 2, and I'm gonna copy first A, right? I'm gonna copy first the A operation for the A elements 1 and 2, and then I'm gonna hard copy the elements in B, which is just 3 because I don't need to repeat the 1. Okay. Now let's do the opposite. Let's hard copy B first and then A. So B, it's 3, 1, and it's here. And then I'll hard copy A. And when I do this, I will only hard copy 2 because 1 is already there. And in the end of the day, look at this. 1, 2, 3, and 3, 1, 2. These newly generated sets are exactly the same. Although they have a different order, it doesn't matter. They have the same objects. And sets are collections of objects. Okay? So this is a commutative property of the union. Okay? The next property is the associative property. And it's exactly the same property for the addition operation when we're talking about algebraic operations. So in arithmetic, you can do like, you could do this. Whatever comes in parentheses goes first, right? The operation that goes inside the parentheses is the operation you should do first. So this means this is 3 plus 3 equals 6. Now, but I can do the same thing. I can do I could do first 2 plus 3, which is 5, plus 1 is 6. So the order here also doesn't matter. The parenthesis doesn't matter. The position of the parenthesis. And for the set operation, union is the same thing. So A union B union C is equal to A union B union C. So what does this mean? This in the left-hand side is saying, well, first do the parenthesis first, do B union C. This is a new set. Okay, this will result in a new set. And then take this new set that is inside the parenthesis and unite with A. Okay, so this is the sequence of operations that operation that we're doing. And the right hand side is the order of the operations are like different. So first you take A and unite with B, and this will give you a new set, this new set here. And then you will unite this new set with C. Okay, so let's say that we had a C with 4, 5. Okay, so let's do first the left hand side, which I'm calling 1. Let's try to do the left hand side. So first of all, I'm going to start uniting B with C, right? So B union C, is it inside the parenthesis, so should be done first. And B union C is, I will hard copy whatever is in B and then hard copy whatever is in C. Okay? Again, it's the take it all kind of philosophy here. Okay. Now, this guy is a totally new set. And what I'm going to do is I'm going to unite this totally new set with A. So I'm going to A unite this new set. So what I'm going to do is I have to look at here at A and at this one, B union C. So hard copy A first, 1, 2, and then hard copy this guy. So I know it's a kind of bulky nomenclature. It's kind of an overloaded nomenclature here, B union C. But in the end of the day, this is a set. This is an operation between sets. A is a set, and B union C is another set. So I copy A, 1, 2, and then I copy whatever is B union C. So it's 3. Should I copy 1? No, because 1 is already here. So I don't need to copy 1, and then 4, and then 5. Okay? So this is the result of the left-hand side of the associative rule there. Now let's try to do it as the other sequence of steps. The pink sequence of steps. In the pink sequence of steps, I first do whatever comes in the parentheses. So now I'm not doing first B union C. I'm doing A union B first. Okay? And actually I already did. It's here, right? It's here. This is A union B. So I'm not going to do it again. But this new set, now I will kind of unite this new set with C. So first of all, I calculate A union B, which is there. I'm just kind of repeating it here so that we have it closer. And then what I'm going to do now, I'm going to take this new set, okay? And I'm going to unite it with C. So again, it's an overloaded notation for a new set, and this is set C. So what I'm going to do is I'm going to take everyone from A union B, which is 1, 2, and 3. And also I'm hard copying C. So C is 4, 5. 4 and 5, okay? So in the end of the day, if you compare the first methodology, right, and the second methodology, it results in the same set. So what this expression here is telling me is that it doesn't matter if you start doing unions differently, right? If you do it in with parentheses here or there, it doesn't matter. It will give you the same set. So the same set. The same set. And let me get rid of this and that. Oops. Okay, wait. So the same set that you are obtaining, you're forming on expression 1 is equal to the set that you would obtain if you would start in a different sequence, okay? Which is the set on the right hand side of the equation. Okay. Well, there's another property of union, which is called distributive, but we will see this. Sorry about that. Okay, but we will come back to it. I'm not going to talk about this right now. Okay, just we're going to discuss this in a bit because we need to learn about another operation named intersection. Okay. So what is the intersection? Again, it's a set operation, so it's an operation between sets A intersection B, and this operation will result in another set that you can give any name you want, or just use the A intersect B notation. Okay, so the intersection is actually depicted here. So imagine that you have a universe or a universal set, and you have set A inside of it and set B inside of it. If you think about the intersection operation between A and B, so the intersection operation between A and B is the blue part, is the blue set. Okay, so I'm forming this guy here forms a new set. I could call it C if you want. You can call it C. And if I were to highlight C, C is the blue part, is this set here. Okay, whatever sits inside the blue part is a result of, is the intersection. And intersection actually means overlap. So whatever elements are overlapping A and B are in the intersection set. Okay, so this new set is the blue set. So whatever sits here, right, sits in the intersection of A and B. Okay, because it sits in A and it sits in B. So if we were to define this, we can take the common elements and kind of put in a new set. So if you have A, if you have A, union B, you're going to form a new set, and this set says just take the overlap of what is in common between both of the sets. Or you can think about that the elements that are common, Or you can think about that they exist at the same time on both sets, okay? So the element, every element of this new set needs to be common between A and B, right? Okay. And so there's also a colloquial word for intersection that when I say consider A and B, or take A and B, your brain should translate that to math words as, oh, this is A intersection B. Okay, it's just a way that we say this in English. Okay. So here's an example. Let's say A is 2, 3, 4, 5, B is 1, 2, 3, and I'm asking about the intersection. So A intersection B. It's a new set, so it's a new set. I'm gonna open my curly braces here, and the thing is, I have to check what is common between them. I have to ask myself when I'm hard copying things if they exist at the same time in both A and B. Okay, so let's say let's start hard copy. Like, what about element 2? Should I copy it to the intersection? Well, if they are common, if they are both in A and B, yes. Okay, so 2 is an element of the intersection because it's in both at the same time. What about 3? Should I copy? Should 3 be a member of the intersection? Well, sure, because it exists in A and in B. Should I copy 4? Well, 4 exists only in A, right? It's not both in A and B, so I should not copy it. Okay, should I copy 5? Well, no as well, because it's just in A. Now let's ask questions about the elements of B. Should I copy 1? Well, it just exists in B. It's not common, so I'm not going to copy. What about 2? Well, yeah, I should copy, but it's already here. And 3, yeah, I should copy, but it's also here. So actually, I've just finished assessing what is the intersection. The intersection are just the common elements 2 and 3. Okay? So there you are. This is the answer. Okay? So if we think about a Venn diagram, we could say that A has elements 2, oh God, just 1 second. It has elements 2, 3, 4, and 5. And B has elements 1, 2, 3. So if you think about it, 2 and 3 are sitting in the overlap. They are actually part of A and actually part of B. So this is the intersection set. It's the new set that I just obtained. Okay? It's just 2 and 3. Or if you want to kind of do highlighting the outline of the set, or the extreme lines of the set, this is set C. Okay, so 2 and 3 are set C, or the A intersection B. Okay. All right, so the intersection operation also has some properties. Again, it's really simple. If you think about arithmetic operators, you can also have a commutative property in set operation. So the intersection holds the commutative property. A inter B is exactly equal to B inter A. It doesn't matter where you start questioning yourself. Oh, let's see, like we did here, right? I say, oh, let's start with 2. And then I went to 3, asking myself if they are common, and then 4. I could have started in B, right, with the elements of B. And in the end of the day, the set that I come to will be the same. Okay. Now, this operation also has an associative property, just as the union. So again, whatever comes inside the parenthesis needs to be the first operation. So here in this first part, I do first B inter C, okay, and then I'll take this resulting new set, and then I make A intersection with that resulting new set. And in the second part, or the right hand side, I first do A intersection B. Then I take this new form set, and then I will do new form set intersection C. Okay. What this equality is telling me is that it doesn't matter where the parenthesis is. The final set will be the same. Okay. And we can I can prove this just graphically using Venn diagrams. I'm not going to do the other ones, although you are welcome to try, and it's not that hard. So let's say I have A, set B, and I have a set C. Okay, so I'm going to try to draw it. Oh my goodness, no, it's too different. Let's try to do something like A, B, and C. Okay, so let's do the first operation, the left hand side. The first operation is B intersection C because it's inside the parenthesis. What I'm going to do, I'm going to do first the operation in parenthesis for the left hand side. Because it comes inside the parenthesis, it should be done first. B intersection C. Well, B intersection C, I will color a region here, and you will see that the region that I'm doing the limits is whatever sits inside this region is it's at the same time in B and in C. Okay. If you think about it, if you're sitting here, you are part of the B circle and also part of the C. Okay. Now this is my newly formed set, and then what I'm going to do, I'm going to do A intersection that set. Okay. So I'm going to take a yellow part, and I'm going to take whatever I'm going to find a region where the elements sit at the same time in A and the blue part. So it should be the little here, the little shape here. Okay. So if you think about, if you're sitting there, you are part of A, you're part of B intersection C. Okay. So this is the resulting set. Now, let's do the same thing here. Let's do with another color. let's do the right-hand side. First of all, I'm going to start inside the parenthesis, and I'm doing I'm starting in another order. I'm doing A intersection B. So I'm going to take the region where A is, the elements are inside this region, inside this set. They are at the same time in A and B. They're in A and B at the same time. I'm just going to do it lighter. Okay, so this is A intersection B. And then I'm going to take this newly formed set, and I'm going to intersect with C. Okay, so if you think about it, you will land this in, I'm going to do it in green. From the blue part, what region would be at the same time? What region the elements would be at the same time at B and at C and A intersect B, or the blue and C? Well, it would be here. Okay. And although my drawing is poorly made, the regions are the same. Okay, it's just that this C guy here is a little bit bigger. But so this guy is equal to this guy, and it means that it doesn't matter the operation you do first. Okay. So because we saw that the parenthesis doesn't matter, sometimes people just drop the parenthesis, and you do it in the order that you want. You can start B intersecting C, you can start A intersecting B, and you could do whatever intersection you want, and the same to the union, right? Because the union also has the associative thing. So sometimes you see it like this, you could see it like this, or you just can see it without the parenthesis. Okay, meaning just choose the sequence of operations you want to do. Okay, all right, now we're going back to the distributive property, and so I'm going to go, and the intersection also has a distributive property. But here we're going to go back to union, and here's the distributive property. Okay? The distributive property is exactly the same as the multiplication. It's exactly the same property that multiplication has in arithmetic operations. So for example, let's say that you have 5 times 4 plus 1. Okay? So this is the same thing as you do a distribution. You do 5 times 4, you distribute 5, right? Then whatever operation you're doing inside the parenthesis plus then 5 times 1. Okay? So this is the distributive property. Okay? Here is the same thing. So when you see this expressions, you will distribute the operations, okay? And the reason I kind of waited to start this is just because now in this expression here, you see that you have mixed operations. You first do the intersection, and then you do a union that intersection. So now we're kind of doing 2 operations in the same expression. Okay, so before we didn't see the intersection, now we saw what intersection is, and I'm not going to prove this. You have to believe me because it takes a little bit of time, and we don't have that time. But you're welcome to try to prove this with a Venn diagram. It's not that difficult, but anyways, what the rule here is this: if you see this expression where you're kind of mixing the operations, And it seems like it's very close to this form, right? Where you have an operation in brackets and the other one out. You will distribute the operation. So meaning that I'll take A union B. So I'll do A union B. It's here. It's the first part. It's the same thing as doing 5 times. So here's the time operator. 5 times 4. Here's the first part. Then you copy whatever operation is inside the parenthesis, which is the intersection. The same here. You copy whatever operation is inside the parenthesis. And then you distribute the other part, which is A union C. Okay? And this is the second part. So you distribute the 5 finally to the 1. 5 times 1, okay? So this is a property. It's called the distributive property because of this kind of a similarity with the distributive arithmetic property. But it's just that you start with distributing the first operation, copying the whatever is inside the parenthesis, and then distributing to the other member, okay? And for the intersection is actually the same. It's just, so let's go to the intersection, and I'm telling you that, well, intersections also have distributive. So if you think about the property, and I'm making up these numbers, it could be anything. Again, you start distributing for the first member, so it's 5 times, and you operate on the first member, 4. Copy whatever operation is in the parenthesis, and then distribute 5 to the other member, and here you are, okay? Now, let's do this too. Let me get to this a little bit lower. Let me see if I can get this a little bit. Let me see. Yeah. So first of all, A inter. So I'm first doing. It seems like the distributive operator. I have an operation in brackets and then another operation out, right? Sorry, in parentheses, and another out. So I'm gonna do the distributive. So it's like the 5 times. This is A inter B. This is the first part. Then I'm gonna copy whatever is inside the parenthesis, which is union. Okay, and then I'm going to distribute to the other member, which is A inter, then C. Okay, and believe me, what this expression here is telling us is that no matter what you do, if you do this operation here, B union C, and then you do A inter that, or if you do first A inter B, then A inter C, and then you unite this, no matter what you do, it will result in the same set, okay? It will result in the same set. All right. So these are the properties. Here is an exercise. I would like you to pause the video a little bit. Try to get 5 or 10 minutes and try to figure out this this exercise. So in this exercise, I have 3 sets. I have set A, B, and C. You can see there are capital letters, and inside there are letters as elements. There are small letters, so element A, B, and C for the first set, B, D, and F for the second, and A, B, F, G for the third. And the question, there are 2 questions, right? Is A union B inter C a subset of A? And is A union B inter C a subset of C? You can notice that we're asking the same set. We're asking 2 questions around the same set. And this is overloaded. It's operation. There are 2 operations happening in one operation. in one kind of expression, it's overloaded, but operations in sets results in new sets. So this is a set, okay? Let's find, and they're the same in both questions. So the thing is, you will have to find A union B inter C, which is the set we're asking, to analyze if this set, right? If this new set, this new constructed set is a subset of A, and if it's a subset of C. So pause the video a little bit and try to get the answer. Okay, so let's try to solve this thing. Let's find this set here, A union B, and then intersect with C. You could do the distributive here, right? We know you could do, but I'm gonna do it like in the way that's here. But you could do. We know that the operation is commutative, so you could do this, right? So the second comes first and the first set comes second, and then this is just, you could distribute this like that, but we don't need, I'm not testing the identities. I just want to find this thing. So whatever sequence of steps you do, you will land in the same set. So A union B, so let's do A union B. A union B is take everyone from A and B. So I'm hard copying A, I'm hard copying B. So should I repeat B here? So should I hard copy B? Well, I mean, it is true that B is part of this, but no, because B is already there. So I will just copy D and F. Okay, so I hard copied A, and then B. Okay. Now what I'm going to do is I'm going to take this set, this is a set, and I'm going to intersect with C. So A union B intersect C, okay, is what? I need to question what are the common items inside A union B and C. So I'm looking here and here, okay? So is A common? Yeah, A is common. Is B common? Yeah, B is common. Is F common? Sure. Is D common? No. Is G common? No. So I am only copying, right, the common. Okay. Now this is the set that I'm looking for. Now let's answer the questions. Is this set a subset of A? So what I'm asking, if it's A is contained, if A union B intersect C is contained in A. I'm asking if this is a subset of that. Well, to be a subset, it means that A must encompass, must embrace, or all elements of this set here should be inside A. Let's check this. Is little a inside A? Yes. Is little b inside A? Sorry, yes. Is F inside A? Well, no. So it can't. So this is the answer. The answer here is no. It's not a subset, okay? Because all elements should be inside A. So there will be a little part that is not inside A, which is F, and so we can't say that the set is contained or that A embraces completely that set. Now, is this set a subset of C? Well, let's check. So the question is if this is a subset of C, if this is a subset of C, or if all the elements of this overloaded set here are elements of C. Let's check. Is A Little a, element of C, well, yeah. Is B, yeah. Is F, sure. So if you think about, C is embracing, C contains this set, okay? Actually, C contains more than that, but it doesn't matter because C is embracing, C is embracing this set. So this is true, okay? This expression is true, okay? All right, so here's the answer that we just did together. And now we did this exercise before. Let's start a new concept. And this is the last operation. Thank God that we have only 3 operations for sets. And the operation is named the complement, okay? Again, this is a set operation. So you have a set and you will accomplish an operation. You will do an operation in that set, okay? And the complement is it's this. Imagine that I have a universal set, and inside I have a set A. Well, I'm gonna color so that we can kind of reason what is the A complement. I'm coloring the set A complement, meaning that whatever sits in this colored area is in the set of A complement. Okay, so pause a little bit, think about what that means. All right, so that means that the complement means take everything from what you're analyzing from your universal set, but do not take A. Do not take anything that isn't A. So take everything, but not A. Okay, and this operation, the nomenclature and then the syntax that we use is A to the C. It's just like I don't know, like 3 squared in arithmetic. This is an operation, right? In you're operating in a single number. It's a single number operator. It's different from double, like 2 number operators. Okay, this is a single number operator, just exactly as this. So the nomenclature is A to the C, which is A complement, meaning that I have a set A and I want to do an operation in this set A, and the result of this operation is another set. Okay, so remember always that when I operate in sets, I will have another set as a result. So this A to the C is take A and operate a complement, and the result will be exactly this green area here, where you take everyone but not what is in A. Okay, so that's what we just did. And you could also think about a universe or a universal set where you have other sets, right? Like B, before we just had A, now we have B, we could have C, we could have D, with crazy overlaps. But when we talk about A complement, you can take whatever. Maybe you will take a part of B, a part of C, but you cannot take A. Okay, you cannot take elements that sit on A. Okay, elements that sit on A. So in terms of definition, a complement of A consists of every element in the universe that is not in A. Okay, and let's do an example. So let's say that we have a universe is equal to the set of numbers, of positive numbers from 0 to 9. And I can describe this, I can list this because this is kind of an easy listing to do, right? I can do that, I can do this. Or I could also use an alternative description where I name my universal set, column, and an English language description, okay? But anyways, I have the universal set, and I have a set A sitting internally, and it's just a number. It's composed of 2, 4, 5, 9. Okay. So the question is, can you find a complement, right? Can you find the new set, because this is a new set that results from the complement of A? Again, let's do the procedure. Take every element in the universe that is not in A. So the question is, let's start with 0. 0 is in the universe. Is 0 in A? No. Should I copy it? Yes, because I don't want to be in A. Is 1 in A? Well, no. So should I copy it? What about 2? 2 is in A? Yes. But I don't want any element in A, so I don't copy 2, right? Let's say 3. Can I copy 3? Well, yes, 3 is not in A. Can I copy 4? Well, no, because 4 is in A. 5 is also in A. So I will just copy 6, that is not in A. 7 is not in A. 8 is not in A. And should I copy 9? No, right? So this is what we have. This is the A complement. And graphically, you could imagine that you have this. So you have a universe which like contains everything, okay? You're taking the complement. So you're taking only this numbers here. Okay? All right. So this is the answer. Okay. Now, unfortunately, in this course, you cannot have formula sheets in the test. So whatever formula we learn, we will kind of have to memorize. And I'm just deleting this because we're going to do it again. This was done already. So there are two useful formulas or identities that are useful. And both of these are called the Morgan's laws, just because of De Morgan, it's the guy who just came up with this. And I mean, although you can memorize, and I'm not going to prove them. I can sketch one of them so that you can see that this is true. But I'm going to teach you like how to remember the formula, but kind of how to work out the formula without having to remember it, okay? So the first thing is when you see an operation, so you're taking an operation first, and then you're trying to find the complement, right? Just as I pointed out there, you will remember this rule. What happens is the complement, you get down the complement. You lower down the complement. So you lower down the complement to the first member, right? So this complement gets down here. Then you lower down the complement for the second member, okay? And whatever is in the middle, you will shift. You will flip. So if this is an intersection, if the U is like the opening of the U is it's below, you will just kind of flip it, right? You will change it. You change the direction. So whenever you see this, okay, this set is the same thing as this. okay, because of this equality. And you can remember the formula, but it's easier to remember like what to do when you see this, okay? And the same thing for the second formula. If the operation now is a union, and you're taking the union and then you're taking the complement, you can actually, this is the same thing as, well, lower down the complement to the first member, lower down the complement to the second member, and whatever is in the operation you're talking about, just flip it, okay? So then you can see the result is here. The whatever you obtain here, you will obtain doing the same thing, okay? You will obtain doing the you will obtain the same thing by doing this different operations. So if you do these operations, you will obtain a set that is equal to this, but you're doing kind of different operations, okay? So again, this is the De Morgan laws. I will do really quickly, like just want to show you that, so that you believe me, that this part 1, the set in 1 is equal to the set in 2. So it doesn't matter what kind of operations I'm doing, they are the same, okay? So this is A and B, this is A and B. I'm going to do the first operation. I'm taking the intersection, first the intersection of A and B, so it's this part, okay, it's this set, but I'm taking the complement. So actually what I don't want the blue piece. I want actually what is not in the blue piece, okay? So what I'm taking is whatever is not in the intersection. I'm taking here, okay? I'm taking here. So this is what I'm taking. I'm taking the intersection complement. So I'm complementing the intersection. I don't want the intersection to participate. I can even get rid of the blue part, okay? So this in green is this in green is the resulting set. It's the final set that I obtained. Now, let's see here. In the second part, what they say is, to take the complement of A first, then the complement of B, and unite them. So let's start with the complement of A. I'm taking the complement of A, meaning I want everything in my universe, but that is not in A, right? So this is A complement. In yellow here, this is A complement, okay? Now, what is the second operation here? Well, the second operation is B complement. So let's take B complement. B complement. So B complement is take everyone, but that's not B, right? So the green one will take some A. It's fine, right? I'm doing them separately. I'm doing like it will take some A, but it cannot touch B. Okay, so this bluish thing here is the operation B complement. Okay. All right. Now, the last thing I should do is I should kind of do the union. So the union is take the blue, right? So take the blues, and take the yellows. So do you agree that the blues and the yellows is exactly the same region as the green? The only thing that you don't pick, right? If you pick everybody, every colored part is this, which is equal, like it's left also here. So this is A intersections, A complement, union B complement. right? And they're exactly the same. They are the same. It's the same region. It's the same set, okay? They're the same set. And you can do the same thing to prove this one. It's easy. You can do it at home, okay? All right, so now we will start, well, not now, but in the next lecture, we will start with counting things, right? Counting things inside sets. I will give you some information. Now that we know what sets are, we will kind of learn how to calculate the number of elements inside the sets, okay? All right, thank you so much, guys. See you next lecture.